So we reviewed basic integration, but now it's time to remind ourselves of the big kahuna, which is substitution. The substitution rule for indefinite integrals is very important and very key. You use it a lot when you integrate, even when you're going on and integrating things at higher levels, which we will do, especially in chapter 8 in this course. You're going to use U-substitution all the time. In chapter 6, 7, and 8, you just will. Okay, so how does U-substitution work? If you have a function u is equal to g of x, where g is differentiable on an interval, and let f be continuous on that corresponding range. In other words, the function exists and is differentiable and all that good stuff, right? So if you are taking the integral of f of g of x times g prime of x, right? So right here, du, then you're taking the integral of f of u du, right? F of u du. See it? Actually, let me just change my colors here just so you can see things a little bit more clearly. So if I make that orange, I'll make this green. Right? Okay, so you can use that U-substitution. Now, let's remind ourselves of how to do this. So you're looking for a function inside such that its derivative, or at least some piece of it, is also sitting inside. So for example, if I want to take the integral of this particular function, I can see right here this function is nested inside another one, which has to happen for u. U has to be nested inside something else. So if I let u equal 9 minus x squared, then what's the derivative of that, right? Du dx, the derivative with respect to x, would be negative 2x. And then what we do is we multiply both sides by dx, the differential, to get du equals negative 2x dx. And to be honest with you, we never really bother with this middle step anymore, right? But there you have it for one time only, just to see what it is. Okay, so what does that mean I can do? That means I can take my integral and I can write it as integral of the square root. Where there was 9 minus x squared, I will put u. Where there was negative 2x dx, I can now write negative 2x dx is du. And then I can integrate that. Now doing this way is called forward substitution. When you're moving forward in the problem and putting the u in, is called forward substitution. This might matter to you in differential equations class if you get there. All right, so forward substitution is that way. All right, and then you just take the integral like you normally would. So this is the integral of u to the 1/2 power du, because of course we all learn square roots are the worst. Nobody wants to work with square roots. All right, so then, well, u to the 1/2 power, I would just raise it. So u to the 3/2 multiply by the reciprocal of my new power, 2/3, plus c, gotta love my constant of integration, wonderful. You can't box that because that's not the right answer, because that's still in terms of u. So you have to write 2/3, and where there was a u, you now put back in what u was, which is called back substitution. So if that was forward substitution, this is called back substitution. You're substituting back in the u. And that's the answer. We're done. Right here. That's U-substitution. It's a very handy technique for basically undoing composite functions for integration. So it's equivalent of the opposite of chain rule, right? So I guess I can make a little note of that up here. Right, because chain rule is how you take the derivative of nested functions. So u sub is sort of the opposite. I'm going to put it in quotes. It's not really, but it's along those lines. It's the integral, or excuse me, the inverse of the chain rule. Or I guess I could say the companion of the chain rule. It's its compatriot. There, that'll work. Right? So chain rule is how we take derivatives with nested functions, with composite functions, right? This is a composite function. One function nested inside another. So to take the derivative, you would use chain rule. Pretty easy. To take the integral, it's much more complicated, but one of the ways we do it is with U-substitution. The trick is that not all things can be used with U-substitution, which we will learn extensively in Chapter 8. Now let's practice some more with U-substitution. So given an indefinite integral involving a composite function f of g of x, see there's that composite again, right? That composite function, one nested inside another. Identify the inner function such that a constant multiple of the derivative appears in the integrand. That's the trick. That does not always happen. So if it's going to work, it's going to have to be there. Substitute u and du and so on. Okay, so find the new indefinite integral and write the results, and then go back. Okay, so this is the back substitution right here that they're talking about. When they're saying write the results in terms of x, right there, that's back substituted. This is only needed for when you're doing indefinite integrals like that. And then what I was just saying, not all integrands yield to the substitution rule. There are in fact infinitely many that do not. We will see more in Chapter 8, and then we will see even more in differential equations in Calculus 3 if we're looking for them. Okay. Oh, and this right here is forward substitution in case you're interested. Oh no, not there. Here. This is forward substitution, sorry. Because you're putting in the u value. This is actually integrating right here. There we go. All right, so let's practice it. We're going to use substitution to evaluate the following integrals. All right, so the thing about u equals g of x is that it's the nested function. It's the inner function. It's inside. So I want to look for a function that's inside another function. And these first two are actually very simple. It's 7x. It's right there. It's nested inside. So u would be 7x. The derivative of that would be 7 dx. Now, when you look at our problem, we don't have 7. So I want to make it be just dx, not 7 dx. So I would say 1/7 du is equal to dx. That's what I have in my problem. So that way when I write the integral, it's e to the u, but instead of dx, I would write what dx is equal to, which is 1/7 du. All right, well, 1/7 can come out in front because we learned a long time ago with constants in integration that we can bring the constant out in front. And then the integral of e to the something is e to the something, right? E to the x is e to the x and so on. So this would be 1/7 e to the u. Everybody loves the integral and derivative of e to the u because it's always e to the u times the inner part. All right, so 1/7 e to the u plus c. There's my constant of integration. So I substituted right here, right? There's my substitution. Here's my integration. That was just me rewriting. There's my integration. If I'm looking for step 4, I'm going to rewrite it back. It's 1/7 e to the 7x plus c. There was step 2, there was step 3, there was step 4, and here's step 1. All right, let's do it again. Okay, so my inner function is rather obvious on this one. It's right there. So u is 5x plus 8. Honestly, we get to the point with these ones because they're simple linear functions like 7x or 5x plus 8. We get to the point where we don't even really write all the work for them anymore because it'll always be 5 dx, so therefore it'll be 1/5 du. It's the slope of this linear function, right, is multiplied by dx, therefore 1/5, 1 over that slope, is equal to dx, always. So this would be the integral of the cosine of u times 1/5 du. All right, well, again, I'm going to rewrite that as 1/5 integral cosine of u du. Okay, so the integral of cosine is sine. So this would be 1/5 sine of u plus c. Love those constant integrations for indefinite integrals. And that would be 1/5 sine of 5x plus 8. And we're done. So there's the figuring out what u is, right? The u, and then here's the substitution part right here. I just rewrote it. There's the integration part, and there's the back substitution part, right? So figuring out the substitution, then substituting, integrating, and then back substituting. All right, let's keep going. So u is equal to, well, this function's nested inside the squared. So u is x to the 4th plus 3. The derivative of that would be 4x to the 3rd dx, right? So 4x to the 3rd, I want the x to the 3rd and I want the dx because they're in there, but I don't want that 4. So I'm going to make it 1/4 du is equal to x to the 3rd dx. So when I rewrite this, just for the sake of it, I'm going to kind of put some lines in here so I can keep my problems separated. Okay, so this is equal to u squared, and then it's multiplied by 1/4 du. Those two letters du, and 1/4 du, has the x cubed and the dx in it. By writing this number and these two letters, we are writing x cubed dx. They are one and the same. Remember that when you've done your substitution, you can't have x's and u's in here. They either have to all be u's or all be x's, but you can't mix and match. Right, so it has to be that your entire x cubed and dx are covered by your 1/4 du, which they are. All right, so this would be 1/4 du, and then it'd be integral of u squared. Okay, well, the integral of u squared is pretty easy. That's u to the 3rd. So it'll be 1/4 sitting out in front. And then I'm going to have u to the 3rd. But of course, we multiply by the reciprocal of that new power. So it'll be 1/3 out in front, plus my constant of integration, which would be 1/12 u cubed plus c, which would be 1/12. And then u was x to the 4th plus 3. Sorry, I lost my color coding there. There we go. All right, last but not least, it can be a little tricky on this one, but remember that this is the same as cosine of x to the 9th times the sine of x dx, which makes it more obvious that the inner function is actually cosine. And then the derivative of that is negative sine. Right? The integral of cosine is positive sine. The derivative of cosine is negative sine. Well, I don't want the negative. So what I want is negative du, because negative du would be sine of x dx. In other words, you're multiplying both sides by a negative. All right, this will work. So then I can say that this is equal to the integral of u to the 9th. And then I would write negative du. Well, a negative is the same as a -1, so I might as well just write that out in front. And I generally do. I'm just putting them in here at this point because it's review. So this is negative u to the 9th du. But the integral of u to the 9th would be u to the 10th times 1/10. So this would be equal to -1 times 1/10, and then u to the 10 plus c. Because of course there's a negative sitting out in front. You could just leave it as negative if you don't want to think of it as a -1. It's not, going to hurt anything, but it'll make it a -1 in a second. All right, so that would be equal to negative 1/10. And then u was cosine. So it's cosine of x to the 10 plus c. Or if you want to be fancy about it, negative 1/10 cosine to the 10 of x plus c. Either one of those is fine.